Okay, the goal is for us to apply matrix methods to do transformations listed there, and this video specifically is focusing in on reflections, dilations and translations in a plane. So you can see in the table there we've got basically a summary, and we're going to show why these things work. So the first one here is reflection in the x-axis. So yes, indeed, we're starting with reflections. So reflection can happen in each of the x or y axes, or it can happen in the diagonals y equals x or y equals negative x. And you can see here we've got a rule and a matrix. So let's explain all that and maybe draw some diagrams. First of all, when we basically are reflecting something in the x-axis, let's draw our x and y axes. And if we reflect in the x-axis here, a certain point xy, we'll have an image in line with, but the same number of units away from the x-axis vertically. So that would come out as x negative y. Now notice as equations we can see that process here. So x dash is the image of what was originally this part of the point, and you can see that basically the x value is unaltered and the y value is not relevant to the x value, so it has a coefficient of 0. And so in an equation we can see the first row of the resulting matrix. Y dash, x is irrelevant to y dash, and we find that the magnitude was the same, but it has a negative sign. So if we could say it's plus negative 1y or minus y, and you can see where the second row of that matrix comes from. Let's generate reflection in the y-axis now. So using essentially like y-axis as the mirror, to use loose terms, we have a line that's perpendicular to the axis, and we go to the same distance to the other side in this direction as shown, and you'll find that basically we have the same y value with the same height above the origin, but the x value is the negative of what it was. So we have negative x, y, and we can see that there we have a negative 1 coefficient with the x and a 1 coefficient with the y and zeros elsewhere, yielding this matrix here. So far we have two matrices with ones or negative ones on the leading diagonal and zeros everywhere else. So there are our two transformation matrices for reflection in the x and the y axis respectively. So for the diagonals, the line y equals x, for example, if we put that in, now it's essentially at 45 degrees to either axis. And if we have some nominal point xy, again, just like previously, we need to remember there are right angles. If we go back to the previous example, and it's certainly also the case for the example before, we are projecting at right angles to the line of reflection. So this one here, we're looking at something that's perpendicular to the line y equals x. Okay, so let me make that very clear that that's y equals x, and the right angle is as such there or anywhere, and we basically will have this distance continue through to here. Okay, now the image is actually interesting. It's y comma x becomes the image. So you can see then that x dash is yielded by 0x this time and a 1y. And the same applies for y dash, 1x plus 0y, and the resulting matrix can be shown. And if we look at the contrast between that and the matrices above, you notice that the ones are not in the leading diagonal anymore, they're in the alternate diagonal. So that just leaves reflection for y equals negative x now, So let's draw that in. So if we've got some nominal point x, y there, and we've got the line y equals negative x, now it's a falling line because of its negative gradient. It's a diagonal going in that direction as shown. And again, we project at right angles to the line y equals x. That will yield the mapping negative y comma negative x. So you can see how the matrix is derived from the equations as shown there, and we have the same matrix as above, except for it has negative ones on that diagonal. Okay, phase 2 out of 3 in the video, we're looking at the transformation dilation. Now, dilation is essentially a stretch. You might have seen that in various studies of functions in some of your other maths that you may have completed. So there are different types. So there's dilations from the y-axis, from the x-axis, and from both. So we're talking about a stretch by a factor. Our old friend the unit square can be handy here. If we have a unit square with 1 by 1, of course, being a unit square with those coordinates, if we have a dilation from the y-axis, let's say it's by a factor of 2, that means we're stretching across this way, and so all the dimensions going away from the y-axis are dilated by that factor, and so we will get the point 2, 1, and so that's our new shape. So the new shape is shown by the shading here. So we show the dilation factor by representing it by c. In this case, c would be equal to 2 if it's a dilation from the x-axis. So that would be given by this first equation is the most important one, cx plus 0y. So that matrix is needed there, and nothing happens in regards to the second equation, so it's 0, 1. Okay, so now we can move on to dilation from the x-axis. We start again with our unit square, which is a very helpful device. If we find our unit square here, now I'm just going to rub out the coordinates I just put in there. You've seen them, and there they go. Because I actually need to dilate this from the x-axis, so from the x-axis, it's going away from the x-axis is one way of thinking that through. And if we look at a dilation again of, let's say it's 3 this time, it's going to be the whole total length now along here is going to be 3 times. So any equivalent point will be moved, stretched by a factor of 3. Its magnitude will be multiplied by 3, and so the new shape would be like that there. And so we would have 1, 3, whereas we had 1, 1 down there. So that's dilation from the x-axis, and hence especially the second row there of the matrix. Dilation from both, we combine them together. So if we look at the above, we can see to get this, we look at dilation from the y-axis, and it's a mixture of the both results from above there. Notice that C is represented by a D here because C does not necessarily equal D, but essentially dilation from both of them is a combination of the two above. Final one is a translation where we're basically moving something. For example, like this triangle ABC. Okay, we've moved it in essentially 2 directions. We've moved it in the x direction and in the y direction. So we can see the corresponding points have moved a certain number of units across and a certain number of units up. And the same instructions apply to all the corresponding points. If they're not, the resulting shape will not be the same. So the shape remains the same. There's no distortion. There's no dilation. It's purely just a movement of position following a couple of instructions essentially. And therefore, when we go back and have a look at something, a translation of A units in the x direction and B units in the y, that makes sense, and it's defined by the rule. Okay, so all of the x coordinates get A added to them, and all of the Y coordinates get B added to them to get the new the image. In the matrix form, we've got X dash Y dash equals XY plus AB. So that's matrix addition. Okay, so just be careful, because up here all of these will involve matrix multiplication. For example, if we want to find, if we're considering this one here, and we start with the 0.34, if we want to reflect 3,4 in the y-axis, reflection in the y-axis for 3,4. Okay, this is probably something you could easily do in your head, but to represent it in matrix form, we basically need to convert that into a column matrix and use this matrix here. So we write this matrix first for conformability sakes, so that they can be multiplied correctly or multiplied at all. So we have a 2 by 2 by 2 by 1. Okay, so we'll get another 2 by 1, and we go okay, so it's negative 3 plus 0, and then 0 plus 4. And that makes sense, because remember, when you were looking at a reflection in the y-axis, as we saw earlier on, okay, which is this example here, if we have xy becomes negative xy, which you can see there. So the point written as a point as such. So basically, when we're looking at all of these examples here for reflection, they involve matrix multiplication. So reflection, the operation is matrix multiplication. Multiplication also applies to dilation. So with dilation, we're going to be using matrix multiplication. Let's look at a quick example of dilation with that multiplication. Let's use our 0.34 that we just used. So if we're starting with a 0.34, what's a matrix dilation from the y-axis? Let's choose that one. We basically need to write dilation by a factor of 2, I should say, too, by the way. So you need to give the dilation factor, otherwise there's not enough information. Okay, so I'll keep it simple. So 3, 4 again is a column vector. So how do we do that? We have to write 2 in the place there. We have 2, 0, 0, 1. Oh, that's a terrible 2. Alright, that's a little bit better. And 3, 4, and we go through and multiply it. And we've got 6 plus 0 is 6. And 0 plus 4 is 4. Notice how it doubled the first part and did not change the second part, because it's from the y-axis, so that will only affect the x. So 3, 4 becomes 6, 4. And lastly, the case of the translation is a simple addition of a constant to x and a different constant to y. So again, if we started with our same point that we've been using, 3, 4, we had to translate it 4 units in the x direction and 2 units in the y direction. We simply would go, so at the moment x is 3, so we go 3 plus 4, comma, and y is 4, so 4 plus 2, and we would have 7, 6,